Sir.
Good evening, Sam.
Good evening, sir.
Hi. Are the others here? It have 40. All right, let the others come and join in. Let us at least start off with the recap and then maybe we can start off with the fresh portion. All right, so in case of our last day discussion, we had started off with our first module, and in that aspect, we have finally found out that we have to consider that a few of the basic necessary components in electronics as well as from electrical, and the understanding of those principles are essential for our knowledge. As we have also observed in our labs, also we have actually started off with those basic understandings, as they are the fundamental building blocks to any of the communication subjects or anything of related to electronics as well. So in that light, we had discussed a very important topic on resistors, and we have found out that the different types of resistor, what are the different types, how are they made of, what are the salient features of each and every resistor and how they are different, what are the salient advantages of few of the resistors and what are the other alternatives to it. So those things we have discussed a lot. And I think if I'm not wrong, we had ended our discussion on the topic that the color coding uh, of of uh, of a particular or some sample register, which again, as for my knowledge, it will be pretty much known to all of you, and I don't think we will spend much time on this, as hopefully when you are coming back over here, we will have a separate hardware related stuff where we can also show you the hardware, the registers itself, and we can find out. We will have to brush up those the color coding there as well. But anyway, in general, what we have observed that for a four-band register is the most commonest of register which are used in lab. And in that, we have observed that the first two bands are ideally the first and the second digits, if you observe. So ideally, these two bands in this photo, if you observe, this is my first one, this is my second one. So these two bands which you are looking at, they are the resistance value. Along with that, the third band that you are looking at, they are the multiplier value, and the last one being the tolerance. And as I said, the tolerance, by meaning by tolerance, is that when a manufacturer is making of a register, so there will always be a scenario that there will be some kind of an offset that will be set in with the measured value of register. So if it is suppose a 10K register, so somewhere it might be 10.2 or 10.3, like that might happen. So that is that portion, that 0.2 or 0.3 difference from the respective value is what we are calling as the tolerance. So naturally, the lesser the tolerance, the better the option we have, or the better the scenario we have. So that's 4-band. Even we have a 5-band register as well. For example, in this case, you can observe that there are 3 bands, first 3 bands, which will be acting as the register value. Then the 4th band will be considered as a multiplier, and the 5th band will be the tolerance. So that is also a very specific set of band registers also. So usually like 200K, 100K, 270K, like that, a little bit bigger values, mostly we will consider all for the 5th range. So based on that, I told you this particular example as well, where I think we have categorically mentioned that how do we read this 270 ohm. Suppose 270 ohm is given. So the first one is 2. So 2 indicates the first band, 7 indicates the second one, and 0 indicates the multiple. Okay, so this 270, the number of times it gets multiplied, it is 10 times it has got multiplied. So let's investigate a little bit, as we had done on last day's class as well. So the first one is a red one, red color. So red as the first band is 2. The second one is 7, or second one is anyway, it's a violet color. So the violet is indicative to 7. So that's why it is a 7. And the third band here is a brown color. So brown is a multiplier factor, which is 10. So that's why it's a 270 ohm is what the answer is. And it is a gold tolerance value, or the 4th band is gold. For the gold, it comes out as a tolerance for 5%. So that's why it is a. So like that, we can actually divide our all the resistors in the different categories based on this color coding. And as I said also on last day that this is a very common, there are many others actually, there are different other nomenclatures in which you can remember the positions of all these color coding. And in that, one of the very commonest one is B.B. Roy of Great Britain has a good wife, has a very good wife. So in that way, you can observe black, brown, red, orange, green, blue, like that. You can remember the position of all the bands one after the another. So that is another trick in its own way. So this is where we actually had ended our discussion with, and in fact, we can go on discussing this also. Like there are these are some of the different examples. Okay, so these are the different examples. So suppose I want anyone to help me out in this. So if suppose I want to, sorry, I want to have a 10K. Okay, 10K. So what should be the color coding that we have to consider? Can anyone?
Brown, black, orange, silver.
Brown, black, orange, silver. Brown is 1. Why it is correct? Let's see. So 1 is brown. Then black is 0. So that's second. And then we have orange. Orange is 10 to the power 3. Okay, so that's why 10 to the power 3 means it's 10K. And then we have a 10% tolerance. So the 10% tolerance comes in for the silver. You can observe at the end. All right. So this is how we actually go on finding out. This is usually helpful when we are doing with the hardware. So that's why it is more advantageous for the other case also. Can someone else can come out with 700 ohm? What should be 700 ohm? The fourth one. What should be the color coding for 700 ohm? Rishabh is there? Rishabh?
Yes, sir.
Yes, sir.
Yeah. Can you tell me for 700 ohm plus minus 10%? What should be the color coding?
Violet, black, and white
It
or
should
silver.
be 4-band. I'm considering a 4-band scenario. So 700 ohm, what should it be? You said violet, then black.
Black, another black and silver.
And silver. Is it correct? All the others? Can anyone tell me is it correct or not? Someone can confirm that?
So violet, black, brown, and then
Violet, black, brown. So why? Because the problem that the previous one had is that if I write it down once again, violet was fine, which is 7. Then as he has pointed out, black. So it should be like 0. But then the multiplier is 10 to the power 0 for that matter. Okay, so that doesn't come into handy as much. Whereas in case of brown, if it is, then it becomes 10 to the power 1. So this gets multiplied by 10 because it's 700. And then we have the plus minus 10%. So which is around again the silver. So it should be a silver somewhere over here. So that's how we are looking at. For your own understanding, I just thought of sharing this. Let me just stop this presentation a while. And this is another site in which you actually can look into. I have presented it over here, the second one. Okay, you can. I'll just copy and I'll just paste it in the chat. Let me just go back to the. And I want all of you, those who are actually having handy with your laptops and all, you can just try your hands out on this. This you can just click on this and you will find that you have come across this particular page. This there are many other sources also, but somehow I find that here you can actually go on testing all your values and all. So suppose you make a color. For example, let us try that violet. We have black. Okay, and we have brown. All right, so this is what we are looking at, and we have a selected color as silver. So this is basically what the answer is which we are looking at. So that confirms over it. Even in this case, the earlier one, if you look at, that would have been a 70 ohm until like instead of 700 ohm. So that's way different. Okay, the resistor values will vary a lot. So this particular site in your chat which I have shared, you can look into it later on for testing purpose, for just to refresh your understanding on this color coding and to get a knowledge of it. Right?
Sir,
Sir,
if we use black, violet, or red, then we still get 700 ohms. So is there any generalization?
No, nothing of that generalization actually. But ideally, we should follow the I would like this. So we have to follow the direction in which these bands are placed. Like suppose you have a four like 300 suppose. So in this the first one and you are we are assuming that we are using a 4 band. So the first letter is 3. All right. So we have to make sure that the first band is orange. You cannot have anything else. Understood. So that is how the trend is. That's why this nomenclature wise, it is like top down approach from black to silver. That is how black to white rather black to white how we have to read all the values.
Excuse me, sir.
Yeah.
So
Sir, here
while
silver
torch,
and white both have plus minus 10% tolerance. Then what should we
No,
consider?
because it is gold and silver are the two only colors for the tolerance. No other colors are for the tolerance. So we
Okay,
have to
okay, sir.
consider the gold and silver. The most commonly used resistors all will have gold and silver only. This white comes with this, but these are rarely used. They are never being used. Only this gold and silver will be there. All right, so this is like you can just go through the slides as well as you can test it on your own with different combinations and all just for your own understanding. As I said, we will come back to this in the hardware and we will test it on our own with the both in terms of viewing it and understanding what is the value as well as we will test it using the multimeter to find out what is the exact value of the and you will find that suppose this 700 ohm that we were discussing or maybe a 70 ohm for that matter, whenever you will find a hardware or a resistor and you test it in multimeter, definitely it will either come less or higher. So it will not come less actually, it will come around like 70.3, 70.5 or even 71 ohm. Suppose you have a 70 ohm resistor for that matter. So that will be the tolerance thing can be tested very easily in labs. Okay, now coming to this part again, very common. I think we can skip this slide as well. That this is just again the recap on series and parallel connection of resistors. And in fact, in our labs, already one of the batch we have started off using this. I have given one assignment. So the other batch also, when we have a lab tomorrow, we will actually go through some more questions on this. So the series and the parallel connections of resistor is a fundamental concept where the when you're looking at the current path, if there is only one path that is available, so all the components must be in series. So as in this example, we can observe very clearly, and I don't think we need to spend much time on this. Hopefully, this is already clear to almost everyone. And this is basically where the circuit analysis comes in. I think this is also pretty much handy to all, but still for my own benefit, for my own understanding, let us just discuss a little bit over here. So if you observe over here that this R1, this particular circuit, and there is a branch, two branches over here. One branch has this R2 and R3, and the other branch has R4. But ideally, we can observe that these two branches, the R2, R3 branch and the R4 branch, these are in parallel in connection. All right, so we have to make sure that these two are in series, R2 and R3 are in series because there's a single path available. So this R2 and R4 will give us R2 and R3 will be added up to get a equivalent resistance, and that equivalent resistance will be parallel to R4. So R equivalent will be parallel to R4, and that calculated resistance will be in series to R1. So we can say something of this nature. All right, and that will be the equivalent resistor that will be there for the circuit where there is a power supply which is placed over here. So that I think I have done a very small little calculation over here. This R equivalent 3.2 because we have R2 as 1K and my R3 is of 2.2K. So that is why it is 3.2K that we are getting. Now 3.2K is parallel to R4 which is 4.7K. All right, so that is how we can go on estimating the calculation. So I'm skipping all this part so that I don't think this is waste of time actually, and we already know this stuff. So let's move on. So similar kind of but although with the assumption I'm moving on that all of you are having a thorough understanding on this series parallel networks, and that's why we are also testing it in our labs and in the assignments also. When I'm going to do there also, we are trying to do it manually. All right, so that is basically the practice I would expect all of you to have, because you can expect a similar kind of question on series parallel combinations or different circuit elements in from this particular module in your exam as well. All right, so that type of this type of questions or even the task questions also can be asked for from yourself, from our side, and hopefully that you might be able to solve them quite easily because you already know this stuff. So that's why the assumption is. And this is again the very conventional formulas. I think that's also is known to all of you. The relationship between EIR and the voltage is given by the current multiplied by resistor and other way round. So if I know about two of the important components, the voltage and the current, we can find out what is the resistive component to the circuit. And in fact, this voltage and current relationship is so important that later on in second module, when we discuss about the semiconductor, where we actually start with the modules on basic electronics, you will find that this VI characteristics will become a very, very important segment of our discussion to test the efficiency of a device. Okay, so that's why these parameters are fundamental, but yet they are used at every point of time, every time when we are going to discuss further. So this concept should be thoroughly understood. So let us start off with our the other circuit component that is also very essential, not only for as a component, but the principle itself. So that is basically the capacitor. Okay, and again, I think from your +2 level, you already are familiar with what is capacitor and how it works. And but still, just to be sure and just to be in the same slide, that we are in a case that two or more parallel conductive metal plates, which are connected, which are not connected or touching each other, but are electrically separated by some kind of a dielectric. If they are connected through a potential, then definitely the charge accumulation will happen. And we know the conventional formulas, as we know that C equals to Q by V, that is the charge accumulated by the voltage, as well as, or you can say that P equal to Q by C. In that way, there are different same set of formulas, we can rearrange it. And in that way, what happens that if I go on changing the potential, definitely there will be change in capacitance. Or on the other way, if the capacitance changes, definitely there will be a change in the potential. So it's a vice versa relationship or an inverse relationship that happens. And in that way, what happens that in many of this electronic circuit, what is the implication of this? Many of the sensors, okay, in electronics, in electronic device or electronics, the touch screen, okay, the mobile phone that you are using, the touch screen that you are using, that is actually a capacitive sensor. All right. So that capacitive sensor is basically a work of the same principle as is being done over here. So as just for example, because again, I'm not trying to avoid the conventional things, what is already there or what you already know. So suppose you have a two plates over here, right? Now you have a finger. Okay. So this is the touch plate. So now this is the distance that we have for a mobile screen. Okay. So now if you are adding a finger over here and you are touching the screen, definitely this particular diaphragm will come somewhere over here. So this will be the new position. So this means that there will be a change in distance d1. All right. Now, as we already are familiar with that, see the capacitance in that way. That is again depending on. Can anyone tell me how the capacitance and the distance and area are interlinked? Epsilon.
Epsilon not A by D.
A by D, correct? So in that way, so if the distance changes, definitely there will be a change in the capacitance. All right. So and keeping the other things constant. So the capacitance, if it changes, as we know again, C equals to Q by V. So definitely with the C changing, the voltage will change. And definitely that will result into some potential differences. That potential difference can also be again measured through some devices. And if it goes beyond the threshold, we will map to a particular touch depicting what the particular voltage level is. So that is how the sensor also works. So that's why capacitor is not only the capacitor as a circuit element is not only the limited usage. It has a wide variety of uses, especially in sensors. All right, so we'll see that in maybe fourth and fifth module, we have those in there, but the principle remains the same. So anyway, so this is basically the circuit diagram, and this is the symbol of it, just like we had it for resistor. We also have a capacitor, and this is basically the formula that I was referring to. Already you must be knowing it, and the units for this also, as you can observe, that is farad. Mostly we'll find microfarads being used in most of our cases. So this is a very commonly used thing, that 1 microfarad is 10 to the power minus 6. You can keep this handy. This might be useful while later on while solving numericals also. That's why the purpose of giving it over here is as that. So microfarad, nanofarad, picofarad. So these are the different abbreviation, different units as expected from with respect to the capacitance, and it is named, as you know, from British physicist Michael Faraday and its contribution to electromagnetism and everything. So this is basically the symbol that we are all associated with the normal capacitance. But again, if it is a variable capacitance, which looks something of this nature, so there will be an arrow which is given. Similarly, if you remember that we had a resistor, and if it was something like this, we were calling it as a variable resistor. The same way here also it applies the same. Okay, so this is basically the basic understanding of capacitance or a capacitor and as well as farad. And I think again I'm assuming that you already know this stuff, that capacitance of 1 farad, what does it imply? It implies the charge of 1 coulomb is stored in a plate on the plate via voltage of 1 volt. So that is how 1 farad is defined. I'm hoping that you already know this stuff, so I'm just keeping it a little bit. But all this will be there in the course material. You can just look into it and can refresh your understanding. What I think you might not be knowing is this part, which is again the different types of capacitors which are present and their construction details a little bit. Again, as we had discussed in resistor as well, that the capacitors also will have specific applications, and based on that we will find out our usage for that matter. So the first one is, there are 3 basic category. The first one of its kind is the non-electrolytic or the normal capacitors, in which the 3 categories are mica capacitors, ceramic capacitors, and paper capacitors. So ideally, the name itself, it suggests that what is the basic ingredients that is used for the plates. All right, so you can see the mica capacitor, the plates of aluminum foil separated by a sheet of mica. So that is why it is mica capacitor. Okay, so high voltage application, range of 5 to 10,000 picofarad. So it's quite a huge range that it provides. Ceramic capacitor, it will look something like this. Okay, it looks something like, you will find it in lots of radio and receivers. If you open it, you will find this kind of ceramic receiver inside. Okay, so ceramic disc, the 2 plates coated with a metal such as copper or silver, and tinned wire lids. So these are the wire lids with entire unit is coated with a plastic. Okay, and they are around 3 picofarad to 3 millifarad. So that is the range in which it works. The other one is a paper capacitor. Even that is also very rarely used in our labs and all. But it is ideally, it consists of 2 metal foils separated by the strip of paper. So that's how it is different. And the paper itself is mixed with or coated with something like a material like a wax or a plastic or an oil, something like that. And like that. Okay, so this is one of the types. These are all non-electrolytic ones. But the most interesting ones, and the one that we usually come across in our labs and all, are the electrolytic capacitors as well as the variable capacitance. Although variable capacitance is rarely used, but mostly the electrolytic will definitely be used. So it consists of an aluminum positive plate and a foil electrode, which has an aluminum oxide, okay, film covering one of the sides. So dielectric is like that, and the oxide is in contact with a paper or gauze saturated with electrolyte, positive and negative. So there are already some charge accumulations on the plates, and it has a relatively low voltage rating. So and that is why it is being used in. You can see that in the electrolytic, what happens that the 2 portion, one is a positive and the other one negative. The easiest way to identify them is that by one is the taller one, the one of the tin lead is taller and the one is smaller. So this again will be very handy when we look into the hardware, when we pick up a capacitor and we can identify that this is a tank capacitor, this is an electrolytic capacitor, so like that. And in that also, I think in the next slide we have it, that in the capacitor, the advantage is that in itself, in the capacitor, the specifications will be provided itself. So the way we were looking at the resistor from the color coding, here also the color coding is there, but the generic capacitor will always have the specification right mentioned in the capacitor itself. So we can see it and we can say that what is the picofarad or what are the value it's given. All right. Similarly, I'll come to that in the next slide. Then we have the other option. So non-electrolytic, electrolytic, and the other one is a variable capacitor, where variation of the capacitance is not frequent. Like in some application, the need for variation of capacitance is not frequent. One setting is sufficient for all the normal operations. Okay, in such a situation, we use a variable capacitor, or sometimes it is called as a trimmer. Okay, so they are like when you are trying to adjust it a little bit from what it the value that it contains. So that's where the variable capacitors are used. But as I said, it's very rarely used in our daily purpose. Most of the time, we'll use the electrolytic capacitor itself. And as I was telling you that here also there is a color print, like color coding also for capacitor as well. And you can see that this is the same way. The first is the first digit, then we have a second digit, then we have multiplier, then tolerance, then we have a voltage. But the thing is, for the non-polarized capacitors, small value, as I said it here is mentioned, small value capacitors have their value printed itself, but without any multiplier. So what does that mean? I think I have do I have a diagram? No, I don't have a diagram. I'll show you the electrolytic itself over here. So you can see that this is the voltage level given. Okay, so the itself in the capacitor itself, it's mentioned that what is the working voltage. Okay, as well as the value of the capacitor is 22 microfarad. It's very unlike to the resistor where you don't have the resistor value written. Even the mica capacitor, which is missing over here, the diagram is missing. There, what will happen that ideally, I think in the next slide, I think we'll have it over here. That sometimes what will happen that we will mention it in the capacitor itself. It will be mentioned as 10. Okay, so like 10, it will be mentioned. If time permits, maybe in the lab, I'll show you the diagram for that, maybe in the next class. So suppose it's mentioned as 10, so it means 10 picofarad. Okay, so if the number written on the capacitor is greater than 1, the value will be in the picofarad range. So otherwise, it will be in microfarad range. So that is the basic uh, understanding from a lab point of view. Okay, for usage purpose. So if the number is of the value, it will be in picofarad if it is greater than 1. Okay, otherwise it will be in microfarad. So example, like if it is 10, it means that it is 10 picofarad. But if it is 0.1, okay, so that means 0.1 microfarad. So this value will be printed on the capacitor itself. So we have to just see it and we have to understand that, okay, this is 10 picofarad. This picofarad won't be mentioned anywhere. That's the idea. Okay. And another very commonly used ones are this one, as you can see here, that if there are 3 digits, okay, in the number, the third digit number indicates the number of zeros to be put after first 2 digits. So if it is like 10-4, like it should be read at 10-4. All it shows is 104. So like this. So 10 and 4, it should be like this. So it means that basically 10 is over here and we have 4 zeros over here, which makes it around 0.1 microfarad. All right, so this is another convention of it. You can see this is our convention. Directly 0.1 microfarad, we can understand. Okay, but if suppose we are using with a third digit as well, the convention we are following, the third digit, we actually can use it something of this. All right. Similarly, you can see if the letter K follows the digit, okay, the value will be called as K picofarad. Okay, so suppose 100K it's mentioned. That means, sorry, 10K if it is mentioned, that means 10 kilo picofarad or 0.01 microfarad. All right, so like instead of 4, if it is K mentioned, so that will be another way of looking at it. Okay, similarly, N or M, it means simple, it's nanofarad or microfarad like that. But again, as I said, this won't be handy until and unless you handle a capacitor itself. And fortunately, when you are coming back, this will again be taught to you, and we will see that how we can read the capacitance and while using it to a circuit. Okay, so but these are the different conventions that usually is followed when we are using a capacitor. All right. And even here you can see for the color, capacitor color coding, very rarely, as I said, it's very rarely we use in a lab. So I don't think we can, it will be easy for us to show you this kind of a capacitor back in lab. But ideally the process is the same. It's the same way, just like we usually do it for the resistor. The same way we can find out what is the meaning of it. All right. So that's it about the capacitor color coding, and as well as the capacitors in circuit, like in series and parallel combination, it's just the opposite to that of what resistor happens. So here what happens that If it is in series, the main objective is that if it is in series, the capacitance, then the plates are far apart, making the capacitance less. So whenever you want to make the capacitance less, you have to keep it in series, and the series connection or the series combination would look something of this C1 C2 by C1 plus C2, which is almost equivalent to what the parallel resistance circuit would look like. If there are two resistors, this is the similar kind of structure of equations we usually have. And when we have a parallel capacitance, definitely the plates are they add up together and they're close together, so that makes the capacitance more. So whenever we have to have this kind of a combination, which is a parallel combination, we will add up the capacitance. So it's just the opposite as far as the nomenclature, if you call it that way. It's just the opposite to that of what the resistors would provide. All right, so that is another set of element that I think we should all be using. As I said, the application of this capacitance or the principle of this capacitance will be helpful sometime later as well. In diodes, we will find out that how capacitance is used for, and also in sensors also we are going to use the principle of this capacitance and how it changes in different forms and shapes. That's the only thing. But as far as component is concerned, that will also, as I said, or as I discussed, mostly we will use the microcapacitor because that's the most commonly used and available capacitor that we have. But also along with that, we are also going to use the electrolytic capacitance as well as tank capacitance for our lab purpose. That we will see sometime. And each of them has their own set of naming and reading also process, which I have discussed today. So, the next thing that I think we should all at least have an idea, I think all of you are pretty much familiar with this as well, that when we are adding the source, because the power supply we are adding up is a very important, it plays a very important role in most of our measurement. And in that way, if it is a DC supply that you are operating with, capacitor will essentially block a DC component. All right, so and that is why it is a very important factor, an important property of a capacitor for that matter, and that is like it will just charge, it will get charged for us, it will move to the saturation, and after that it will just get blocked, like it will just cut off the whole process of charging. And hence what will happen that for any given circuit where you want to like you want to block the DC, okay, some spike or something is supposed to come in, you want to block that, okay, all those cases the capacitors are used in a very essential manner, I would say. But on the other hand, when you are looking at AC current supply, definitely it's a the DC current or the blocking will never happen, because AC current, as we all know, I don't know, I think all of you, I'm assuming all of you know the process of AC current and the equations associated with it. So in case of AC current, what happens as the current is changing, as the cycle is changing, that first cycle the capacitor gets charged, whereas in one direction, whereas when the cycle changes of the source itself, then it starts to discharge to the reverse direction. In both the cases, what happens that the charging and the discharging happens not simultaneously but alternatively, and hence it will allow the AC to appear through the capacitor. So the capacitors can be easily used for appliances where there is AC and all. There is no problem at all. It will allow the AC to come, but it will definitely block the DC component whenever it comes. It is a very common usage. I would ask, like I would just tell you so that you can also search on your own. The mics that we use, the condenser mics we use, like the one that is used for very common, like any mouthpiece that you are looking at. So they are called as condenser mic. In those condenser mic, we actually have the same principle of capacitance, where the diaphragm actually changes, the acoustic sensors, it changes based on how we are speaking. Right. So based on that, the capacitance, the plates will vibrate, and that vibration will give rise to some kind of a voltage difference, and that will be an electrical signal. Ideally, that's what the acoustic sensors work. But ideally, what happens in the condenser microphone, there is the output where there is a chance of this possible DC fluctuation or a DC pulse. So there we actually can block it by a coupling capacitor, where it will actually block the DC input to the out, like will block the DC coming in to the respective circuit. because the all of the circuit is working in terms of the output is measured in an AC, suppose in a device, a variable current, but suddenly if there is a DC spike, it will be problematic. So that's where the capacitance is used. That's a very common usage of this particular property. But this is just a one of the case based on the applications and all. So this is the capacitive behavior, I call it. And the last component that I think we should also know, and that is the inductor. Okay, and again, as I said, like it's again, hopefully all of you will be knowing it. So an inductor is a passive electrical component and a very easily built component, I would say, and that opposes the sudden changes in current, and that's basically the idea. If anything that can block or that will oppose the sudden change in current, that is a good option to have it in any circuit. So that we'll see that in one of the animations also. So inductors are also known as coils or chokes because it will block unnecessary increment or uncontrolled increment of current. And I think all of you know the principle. I'll just ask you on that. So inductors, basically it's used to slow down the current surges. You can see over here, it slows down the current surges or spikes by temporarily storing energy in an electromagnetic field and then releasing it back into the circuit. And that is what makes it so useful for any given circuit. Because if you observe that each and every electronic equipment, whatever we come across, okay, they are all like they are connected to some power supply, and definitely in those power supply there will be some spikes, some surges will come. If you don't have an inductor placed properly or not in proper sync with the circuit, definitely the components or the electronic components will get damaged. Okay, so that is the biggest and the most important usage of inductors. We can observe that even with capacitors, like capacitors, inductors will temporarily store energy. But unlike capacitors, inductors store energy in a magnetic field and not in an electric field. So that's, I think all of you know about the Faraday's law and all, how it works. And I'll ask you after this slide, I'll ask you. So the fundamental principles behind the electronics that helps this thing happen is that moving electrons create a magnetic field. And when a moving magnetic field or the changing magnetic field will cause some kind of an electron to move. All right. And that electron, if the inductors, like inductors has the problem with the change in current. By this changing of current, there will be some amount of EMF or that will be generated as the Faraday's law suggests. And that EMF will eventually will oppose the very source that has produced it. Right. So that is how it will be helpful for the uncontrolled to control the ever increasing power surge. Let's see with the diagram. We'll come to this types maybe. I'll come to this first, or maybe the diagram. Yeah, this I think I'll show you first as we are discussing the process involved. So if you observe carefully that whenever we are applying a supply over here, whenever we are applying a supply, suppose what will happen? I might ask you. Let's see how much of understanding you have. Suppose I don't have a inductor over here. Just listen to this question once. If you don't have an inductor over here, what will happen if I apply this supply voltage that way? This is a bulb connected over. Okay. So suppose I don't have an inductor over here. So it's simple. What will happen when you are applying a battery without any trouble, the light will glow. All right. But can anyone tell me, although it's in the animation, it is not that clear. If I add an inductor over here, what changes should be observed when the switch is on? Suppose at this condition. Can anyone tell me?
The light isn't immediately at full brightness.
The light. So my question is, suppose this switch, this is the symbol of a switch actually, this arrow. So if suppose it's closed and I have an inductor over here and I have connected a battery supply over here. Now when suppose I am drawing it on my own, like for my own purpose, suppose this is the scenario at the first case. So this is my bulb and this is connected like this. Suppose there is a switch like this, which is connected right now. So the initial case, what will happen when you are giving a supply, the battery will glow. Simple. All right. And if you remove this switch over here, the circuit will break and it will not, it will like be switched off. Simple. But my question is, like, if I add a inductor somewhere in between like this, okay, just like in this diagram, how it has been added. And now if I make this circuit to work, like if it is a closed circuit, at the initial stage when we are applying a supply, what will happen? Will the bulb glow, or will the bulb won't glow? Or if the bulb glow, will it be immediately it will glow, or it will take some time to glow?
Or after a lag.
After
Sir, it will take some time.
yes, it will take some time. And can anyone explain me why it will take some time?
So means the brightness will be low and then gradually it will become constant.
And how do I relate that? How do I relate that? Can someone also can come in?
The sudden change in current will be opposed when
So,
when the switch is turned on.
Yes, and I think we are all at the same page with this particular famous equation that we all have. That from the Faraday's law, that the induced EMF is somehow negative, like it is opposing, that's why negative, based on the flux that is getting changed because of this power supply that we are adding up. So all throughout this inductor, there will be a flux linkage, which will go on, keep on changing. But as per the Faraday's law, there will be an EMF which will oppose the change in current. So ideally what we can say, this is also equivalent to di dt, or change in current if I call it, and given by minus L. That is a constant, proportionality constant. This L is nothing but the inductor. Basically, if I want to understand this, that whenever the supply is being added and when we have an inductor in between, then definitely the answers, all of you, whatever you have given is absolutely correct. It will take some time. After that, it will start to glow. Okay, and after a certain period of time, it will start to glow, and that too, if you observe that more the current will change. If suppose I want to make this, this has a 5-watt bulb, suppose, and the power supply is feeding in more and more current so that it glows to its full extent. So the more the current it will feed in, the more the more induced EMF will keep in. So that will make this is positive and this will be negative. As this is positive and this is negative, this will act as a limiting circuit or a limiting element in order to make this bulb to glow at a rate which is much lesser compared to when it was standalone, like it was not there, the inductor was not there. So there will be a time lag after which the glow of the bulb will come in. Also, my second question that comes in over here, and that is in fact why it is called a self-inductance. I think all of you know that, because here, can anyone tell me why it is called self-inductance? Why it is called self-inductance? Anyone? Have you ever heard the term? Self-inductance, because the coil itself is the inductor and it is itself opposing the very source. Okay, so that is why it is look like it's because a change in with respect to current and it's opposing happening at the same time in the same coil. So that is why it is called as that is why it's basically called as a self-inductance. All right, so this is called as self-inductance, this L itself. So in that way, just give me a moment. Give me a moment. Just give me a moment. Yeah, so that's why it is called as a self inductance, in fact, and the principle, and that is being mentioned over here itself. All right, so I am not going through this detail. You can look at it later as well, and you can see the graph over here. After a certain period, it gets saturated. So this time versus current also. So this has been explained over here as well. Okay, the same thing has been explained over here as well, that L is given by N d phi dt. Okay, and there should be a minus in fact, and that L is, in a way you can call it as N d phi dt as well. And also the inductance also depends on a number of turns, many factors. There are many factors in fact in which inductance will change, and that is given by the number of coils. You can see the points here, number of coils turned, diameter of the coil, spacing between the turns. So all these are important. All these are important. And you can see here, this coil, so this is wide spacing. Okay, so wide spacing means that it will be a low inductance. If it is a very tightly spaced, it will be meaning a higher inductance. So we can just simply put an inductor with a very tightly knit coil, it will induce a higher inductance. Whereas if you put an in between a core somewhere over here, okay, some core, iron core over here, that will also use as a higher inductance. Okay, act as a higher inductance. So typical inductors values used in electronics are in the range of millihenry to microhenry, like some amount of microhenry, and that is the unit of inductance. I guess all of you know that. And these are the different parameters in which the inductors will work. But mostly again in our labs setup, when we are coming up with this component, we will only use the air cladding only, or air core low inductance itself, and that is sufficient for our understanding. Okay? But most of the in radio receivers and in some of the electronic equipment gadgets, you will find the core, soft core, iron core will be there for that matter. But again, that depends on the usage and how you are using it. So this is also another formula, as you know, that the area and number of turns, how they are related. So L is the inductance, as you know. So mu is the permeability of given over here, permeability. N is the number of turn, A is the area, as well as L is the length of the coil. So all this is given over here, based on which it can be found out that what is the final outcome of the inductance. Okay, so that can be used for the equation that we are referring to over here. So based on a fixed inductance, we can find out what is the amount of change in current that happens. Now, if the source, okay, if it starts to understand that, so it will not try to make the rapid change in current that much, so that though eventually the EMF is lesser and the bulb, in fact, or the circuit works in a perfect manner. So, but now my question is, the final question before we end is that, can you tell me, after, suppose I have a scenario like I had drawn it previously, that suppose I have this particular condition, exactly at this condition, when the switch is like this and the inductor isn't working and it is also glowing like anything. Okay, now what would happen? Okay, what will happen if I suddenly open this switch? Can anyone tell me what will happen? It is glowing full potential, like the bulb, whatever the source, it is working in a full specification. And I have an inductor over here. We have a supply and the switch was closed. Now suddenly I open this. Can you tell me what will happen to the light source over here?
So it will gradually lose its brightness
And
and switch off.
anything else? You will actually get a spark in this particular area. Why? Because you can see the supply is there, right? So the EMF which will be generated by this particular inductor, and it will try to oppose the source in the same way. When the power supply is cut off, it will eventually favor the connection, or it will try to make sure the bulb glows even after that. So in the process, what will happen? There will be a spark that will be generated over here in this switch. Okay, so that will happen. If time permits, I don't know whether we can work out some way in which we can test this whole thing in labs and all, but that is how it happens. Okay, ideally. So this, in fact, the other one, the last half where we end our discussion is the mutual inductance, when AC current is applied to an inductor. Okay, and during the first half of the cycle, the magnetic field builds as if it is like a DC voltage. But during the next half cycle, because it's a sinusoid, so the next half cycle, the current is reversed. And the magnetic field first has to decrease and then the reverse polarity needs to step in. All right. So this process, depending on this value of inductance, this force can work against each other, making for a less than simple situation. What is the situation? The magnetic field surrounding an inductor, you can see over here, the magnetic field surrounding the inductor can cut across another inductor in close proximity. Okay, so this will influence the next one over here. And changing the magnetic field in one can cause the current flow in the other. So this mutual inductance, what is happening? this is where the inductance is sweeping to the next inductor, which is in close proximity. And that will change in current, and that will eventually make this lamp glow. This process that you are looking at, is basically the fundamental principle of the transformers, which is an essential equipment for any power supply that you are coming across. The household current and supply everywhere, you will find the transformers are placed. The basic principle is working on the behavior of a mutual inductor. This is called as mutual inductance because one is affecting the other. So that is why it's mutual. The earlier one was self-inductance because it was affecting itself, EMF itself. But here, one EMF is actually, see in this case, in the bottom half it's mentioned, applied current induces EMF across the inductor, and that will eventually influences. Take a second inductor near the first inductor, flux links with second inductor, which induces the voltage. Okay, so that is how we are coming across the mutual inductance as well with the inductor. But again, this is beyond the scope of our discussion as such. So I just thought of this is just like we had a capacitor behavior we had discussed. So same way the inductor behavior I thought of telling you, so that like in case of capacitor behavior we had a DC and AC, right? It blocks the DC, it will allow the AC. Same way here for the AC supply, it is actually the mutual inductance that will happen, and eventually that will be one inductor will help the other inductor in close proximity to have a current flow through the circuit that it's connected to, and that's the advantage of it. So in summary, what we can say that a resistor, capacitor, and inductor, these are the three basic components that we have discussed. And in that component, you can observe that these are the relationship which we had expressed. In fact, you can observe that the resistor and the inductor has a very similar kind of nature of equations, and the relationships are same, and that's what we had discussed. All right, so let us finish off on that note. We have a different module over here, and we also are running short of time as well. So when we come back on next day's class, I would finish up the first module, and hopefully we can start off with the second module as well. And I would request all of you to please go through the material. I'll upload the material once again today, as well as if you find any relevant material which helps you in understanding these basic concepts, please go through it, as well as try to, I will also give some tutorials or some solved out examples on the series and parallel connections for resistors, in fact. So try to solve those things, because already those things have been done by you, and we don't have the time and luxury to go through all those things in greater details. Apart from this, I would give that responsibility to individual so that you can make up your own mind, you can practice on your own, so that you can expect or you can solve questions relating to that. All right. So you can leave the meeting. I think already I have overshoot. Thank you, everyone. Thank you for your patience.